Okay, last time we looked at few things, mainly the shear, and we looked at an example as well. Then we looked at why we have to provide some reinforcement, transverse reinforcement in flange beams. Then we looked at how we can calculate that. Then we also looked at the minimum amount of reinforcement that has to be provided in any reinforced concrete member. And it depends on the strength of concrete. For 30 megapascal, it's 0.0015, and for 25 megapascal concrete, it's 0.0013. And in addition to that, we learned how to calculate the shear resistance of without reinforcement, without shear reinforcement. And to calculate this, in the case of slabs, we have to consider the average. So we have to consider the average reinforcement ratio. And then we also looked at the punchy shear perimeters that we have to consider. And then we did discuss how to determine the punchy shear capacity. We also learned that, you know, if the shear stress exceeds this value, then there will be crushing failure of concrete. So concrete, the shear stress cannot exceed this value. Then for different, we know the depth, the shear capacity depends on this K value, and K value depends on the depth of the section. So the shear capacity actually depends on the depth of the section and the reinforcement ratio. So for 30 megapascal concrete, this particular table is available, table 8.2. On the other hand, if you want, you can just use the basic equation and calculate the shear capacity. And to use it for different concrete strengths, then we have this modification factor. So these for 30 megapascal concrete. For any other concrete, you have to use the corresponding factor from this particular table, from this table. So in addition to that, so when you have a reinforced concrete member, you have to provide the minimum reinforcement. In addition to that, you have to check the stress under permanent loads, and based on that, you can work out the maximum diameter of the bar needed or the maximum spacing that can be allowed. So today we'll use this particular equation, and to find the permanent load induced stress or the stress induced by the permanent loads, we consider these load factors. So here we say 0.3 times QK plus GK divided by 1.5 QK plus 1.35 GK. So we'll be making use of this particular equation today. And then we also looked at an example on how to calculate the punching shear reinforcement when the punching shear reinforcement is needed. And we learned that, you know, we have to provide the last perimeter within 1.5 D of the perimeter that you no longer need punchy shear reinforcement. And also, if you are providing punchy shear reinforcement, the maximum spacing between two successive punching shear reinforcement uh, arrangement will be 0.75 D. So that's what we covered last time. And out of this, some of these will be used for today's lecture as well. That is what is relevant to shear. So today we'll look at, we'll start from basics and start looking at how to design an isolated pad footing. And then we look at an isolated pad footing first subjected only to the vertical load, axial load. And then we see how to deal with the situation where we have axial load and bending moment both. And then we look at a combined footing. And then we look at what we call a strapped footing. So if you look at an isolated footing, so that's the simplest that you can always encounter. There can be few types of failures because, you know, because of the axial load, there will be a pressure underneath. And because of that pressure, you can have some shear failure here. Or on the other hand, you have to provide adequate reinforcement to carry the flexure on the face of the column. In addition to that, there's a possibility for punching shear failure. So we have to check that also. And then when you are providing reinforcement, you have to provide reinforcement in such a way that the crack controlling rules are complied with. And also the minimum reinforcement that you have to provide here is the minimum specified in EC2. So you have to provide the minimum reinforcement or more. And then you also have to make sure that you comply with the crack controlling rules. And the crack controlling rules have been derived for 0.2 meter, 0.2 millimeter, 0.3 millimeter, and 0.4 millimeter crack widths. And those values are given as table 7.2 in Eurocode 2, table 7.2. And what I have shown earlier is only an extract because we are interested only in 0.3 millimeter crack width. So basically what you have to do is, first you have to select the size of the footing, and then we have to design all the other parameters. So we'll look at this in little detail because we'll be making use of the same method in all the other types of bases. So the first thing that you have to say is that, you know, there will not be a crushing failure due to this crushing failure of concrete due to this column trying to punch through the base at this column face, So that is the crushing failure of concrete. So how we make sure that the crushing failure of concrete will not occur due to shear is by checking the maximum shear stress carrying capacity or maximum shear strength of concrete. And to do that, we have this equation or else last time we looked at this equation. The maximum shear carrying capacity is given by this equation. So the same equation appears here. Where new one is 0.6 times 1 minus FCKO to 150. And then once you check this at the face of the column, then you know whether the selected thickness is sufficient or not. If the selected thickness is sufficient for this particular check, then you can do a approximate check for punching shear resistance. And if the punching shear resistance is also okay with the selected thickness, then you will be able to do detailed calculations. So First calculate the bearing pressure, then see whether the column can fail at the face, then also check whether there can be a typical punching shear failure at the control perimeter. And for these bases, the control perimeter is at 2D from the face of the column. And then carry out a preliminary check on the punching shear just to see whether the thickness selected is adequate. And then if the thickness selected is adequate, then you can determine the reinforcement requirement. And then you can check it for punching shear, direct shear, and then you can also see whether the reinforcement is provided properly to ensure that the crack widths are within limits. And also when you are providing reinforcement, it's important that you know all this reinforcement is anchored at least one anchorage length beyond the face of the column. So the reinforcement should be anchored beyond the face of the column. And if it is not properly anchored, then you have to bend it upward and anchor it. Which does not happen very often because you will find that if the base is small, you will be using a small bar diameter. If the base is large, you will be using a large bar diameter. So generally the anchorage length would be about 40 times diameters. It's slightly lower, but around 40 times diameters. So because of that reason, you will find most of the time this requirement on anchorage can be satisfied easily. So to check for punching shear, we check at a perimeter 2D away from the face of the column. And to check for direct shear, we check at a straight edge, an effective depth away from the face of the column. And when it comes to bending, we check at the face of the column. We check for bending, we check at the base of the column. So those are the three checks that you have to do. Once you have decided the size of the base and the corresponding pressure acting at ultimate loads. So this is an example that I have taken from a book. So we'll just discuss that just to get ourselves familiar with the process so that we can use the same techniques in the other types of bases as well. So when you have footing, the footing is required to resist a characteristic axial load of 1000 kilonewtons, and that is the permanent load, and a variable load of 350 kilonewtons. The size of the column is 400 millimeters square, and the soil is reasonably strong, 200 kilonewtons per meter squared, and that is kind of, you know, hard laterite type soil. That means the laterite soil with less clay will have a bearing capacity of around 200 kilonewtons per meter squared, and characteristic strength of concrete is 30, and characteristic strength of steel is 500. So this is the figure 10.6 that is referred in this example, and the size of the column is 400 by 400. So what we have to first do is, you know, we have to select the size of the footing that we like to have. So what we can do is we can add 1000 and 350, that will give a total of 1350. But when you are designing for bearing, it's important that in addition to the loads that will come through the column, we have to consider the weight of the base as well. We have to consider the weight of the base as well. So to determine the weight of the base, first we have to see what is the size of the base. So if you look at the load, and that is 1000 kilonewtons of dead load plus 350 kilonewtons of variable load, and then if we allow about 10% for the weight of the base, so we can multiply it by 1.1, and then divided by 200, that is the bearing capacity available. Then we get 7.4 meter squared as the answer. And if I take square root of that, you can see the value is 2.7 meters, 2.7 meters. So what I can do is I can select 2.8 meter by 2.8 meter square base. I can select 2.8 meter by 2.8 meter square base to transfer this load of 1000 kilonewtons permanent load and 350 kilonewtons of variable load, and then another about 135 kilonewtons have been allocated for the self weight of the base. And here what happens is when you are designing the bearing capacity, you have to always consider the weight of the base in addition to all the other loads that are coming from above. But when it comes to design the reinforcement, the weight of the base will not cause any bending moment because weight of the base is transferred directly where it comes. So because of that, the weight of the base will not cause any bending or shear in the base. But when it comes to bearing, we have to consider the weight of the base. So weight of the base has to be considered when we are dealing with the bearing, whereas when you are calculating the bending moments and shear forces, we don't have to worry about the weight of the base. The reason is the weight of the base is resisted where it comes. So because of that reason, we don't have to worry about it. So if you look at the service load, with here the calculation has gone with 150 kilonewton allowance for the weight of the base, and this 2.8 meter by 2.8 meter. So when you are selecting the thickness, you have to select the thickness in such a way that the punching shear failures can be prevented, and you have a reasonable margin against punching shear failure, which means automatically you will end up with reasonable thickness. So the size of the base has been selected at 2.8 meters. And then you have to look at what are the factor of safety you have to use. When you are dealing with the structural capacity, then we use for permanent loads, we use a factor of 1.35. And leading variable action, we use a factor of 1.5. And then accompanying variable action, again we use 1.5, but we can have another factor that is something like 0.7 or 0.5, 0.5 for wind load and 0.7 for live loads. So you can actually use this particular combination. But if you are dealing with the situation where you are interested in the deformations of the structure and so on, then you will be looking at this particular combination. And here you can see they are all kind of service load type. But when it comes to the leading variable action, you can have 1.3. But if you are checking the equilibrium of the structure, then you will be using these factors where whatever the force that is unfavorable will be multiplied by 1.1. Whatever the loads that are going to restore the structure, they are favorable actions, we will use 0.9. And when you are checking the stability of the structure, then the variable actions, you will use a factor of 1.5. So basically, the permanent action is there always. So if you are checking the variable action, so say the lateral load, say the variable action is lateral load, then you use 1.5 for overturning, whereas to restore you use 0.9. So these are the factors that we generally use for foundation conditions. So from this table, you can see now when you are designing the pad footing, we will be designing for this particular action 1.35 GK plus 1.5 QK. So the combination one gives the largest force, and you can see the maximum axial load that will be acting in the acting through the column will be 1875 kilonewtons. And if you divide this by the area of the footing, then you will get the soil pressure acting on the footing at ultimate limit state loading. So this is the pressure acting upwards. So the first thing you have to do is, because the thickness has been selected, first we have to see whether the punching shear failure can occur due to compression failure at the face of the column. Due to compression failure at the face of the column. And to do that, we have to find the maximum shear resistance. And if you look at this, the maximum shear resistance is given by the maximum shear resistance is given by this particular expression as given in clause 6.4.5 of EC2 part 1.1. The maximum shear resistance is given by this value, and the value of nu is this expression. FCD is FCKO 1.5. So you can actually find the maximum shear carrying capacity. And if you want the stress, don't use UD. If you want the force, use UD. Multiply this by UD if you want the force. If you want the stress, simply use this equation. Don't multiply it by UD. So depending on whether you are interested in finding the stress or the force, you can see what to do. And here we are interested in the resistance, that is the force. And you have to look at the perimeter. Perimeter is the perimeter of the column. Perimeter of the column is 400 multiplied by 4. Perimeter of the column is 400 multiplied by 4. And the effective depth is calculated as 520 millimeters because it has a total thickness of 600 millimeters. So the effective depth has been selected as 520 millimeters with 50 millimeter cover in the for the bottom reinforcement. And then you can see that when you substitute 520 and 30 megapascal concrete, you can see to cause crushing failure of this 30 megapascal concrete with a column of 400 by 400 is 4,393 kilonewtons, and this is well above 1,875 kilonewtons maximum load that is acting through the foundation, that is acting through the column onto the foundation. So I have again included this VRD max equation and that we have substituted here. This is just just to give you the information on the equation. So basically there's no punching shear failure at the face of the column. Now we have to see what is the punching shear failure at the at a control perimeter 2D away from the face of the column. So basically you have to look at the punching shear failure. So basically when you look at the punching shear failure, we have to worry about two parameters. So this is the column, and here you get 2D. One is the length of the perimeter. So it is C1 and C2. So the length of the perimeter will be 2 C1 plus C2, 2 C1 plus C2 plus 2 C1 plus C2 plus these at a distance 2D. So that is 2 pi r to r is 2D. So that is 2 C1 plus C2 plus 4 pi d. So that is the perimeter U. Perimeter U is this equation. Then to calculate the area, if you want, you can say the area that you are interested is C1 multiplied by C2 plus 2 C1 plus 2 multiplied by 2D, and two of them plus 2 C2 2D plus pi r squared. R is 2D squared. So that is one way of writing the equation. And if C1 is equal to C2, then we can say this area is this area minus this one. So that is C plus 4D, these 2D, C plus 4D squared minus then 2D multiplied by 2D, one of those multiplied by 4 minus so those 4 minus this area, and that is pi r into 2D. You can write it that way also, and this way or this way you can decide the area required. So you will find that the equation used is the second one. So here you can see the equation used is the second equation, and whatever the equation you use will end up with the same answer. So the area of the perimeter is 5.22 square meters, and the area surrounded by the perimeter is 8,134 millimeters. Then the important thing is, when you look at this base, so punchy shear perimeter is somewhere here. So there's a load acting downwards and there's a load acting upwards. So the punchy shear will be caused by the difference of these two. Punchy shear will be caused by the difference of these two. So there's a force downwards and also force upwards. So because of this is a substantial force. In the case of designing the bases, we have to select, you have to use only the net effect. Net effect is the vertical downward force deduct minus the vertical upward force. So you have to get the difference. And so you can see you have to select the difference in force. So that is 2.8 squared minus 5.22 multiplied by 239. So although the total axial load is 1875 kilonewtons, the force that causes punching shear is only 626 kilonewtons. And for this load, we have to see what is the punching shear stress, and you can see the punching shear stress is only 0.15. Punching shear stress is only 0.15, and we know in concrete the minimum shear even with 25 megapascal concrete is in the range of 0.35 to 0.4 range. So if you are getting a value like 0.15, there cannot be any problem with the punching shear failure. So which means the selected thickness of 600 millimeters will be adequate. Selected thickness of 600 millimeters will be adequate. So when you know the thickness, then we have to see what is the bending moment, and the bending moment is due to a load. This is 239, and this is x. So the bending moment will be 239 multiplied by x by 2. So that is the bending moment, and the shear force will be, if you are taking the shear force d away, the shear force will be whatever the shear force that will act here. The shear force will be whatever the shear force that will act here. So we have to see what is the value of bending moment. So bending moment is equal to 239 multiplied by the width of the base, because over 2.8 meters this force is acting. So you are multiplied by the width of the base multiplied by 1.2. The total size is 2.8. 2.8 divided by 2 is 1.4, and then the size of the column is 400 by 400. So you deduct half the size of the column, and that is 1.2 meters. So from the face of the column to the end of the base, we get 1.2 meter distance. So the bending moment can be calculated. And once you know the bending moment, you can calculate m over b squared. Or on the other hand, in this problem, what is calculated is the maximum moment carrying capacity. So the maximum moment carrying capacity is 3,792.93, but the moment that we get is only 482 kilonewton meters. And one thing that happens in this kind of thick bases is most of the time the lever arm Z is 0.95D. Lever arm Z is 0.95D. So we know how to calculate the lever arm, and it's 0.95D. If the lever arm is 0.95D, we can calculate the reinforcement. And once you know the reinforcement, we have to make sure that this is greater than the minimum reinforcement needed. But let's assume that this reinforcement is okay. Then we need 2,243. And if we are using a 16 milliliter bar, the area is 201. So we need about 12 bars. So we need about 12 bars. And 2,800 divided by 11, say 2,700 divided by 11, will give us a spacing of about 245 millimeters. So basically you might end up with 12 bars or 13 bars, but the spacing will be something like, 2700 divided by 12. There are 12 bars because we can keep little space on the sides as well. So you can actually go for 225 millimeter spacing. So 12 bars can be provided at 225 millimeter spacing, because at the very edge you don't have to provide a bar, so it can be little inward. So because of that, you might be able to manage with 12 bars. Sometimes you might need 13 bars as well. So anyway, the area provided is 2412, and then you have to see whether it satisfies the minimum requirement, and that is 2100 ASOBD. Breadth is 2800, depth is 520. So you'll end up with 0.16 as the ratio 100 ASOBD, whereas the allowable value is the minimum requirement is 0.15, as you can see in this particular table. You can see the minimum is 0.15, 0.0015, whereas the amount of reinforcement provided is 0.00165. So because of that reason, you can see for bending, this reinforcement is adequate. Then when you know the reinforcement, the other important thing is to make sure on one side you have the minimum reinforcement, the other side you have the bar spacing. So you have to decide what is the maximum bar spacing that can be provided for this particular reinforcement. So maximum bar spacing or the maximum bar size, one of them. Because there are two tables given in Eurocode, you have to satisfy one of them. You have to satisfy only one of them. So to determine the maximum bar size that can be used, we need the service stress. Service stress is, under the permanent loads or sustained load, what we call quasi-permanent load. That means, almost permanent loads. We are supposed to find the stress in steel. At ultimate limit state, the stress in steel is 500 divided by 1.15. But then what we do is, we consider the ultimate load, we consider the probable service condition, and that is the permanent load plus 30% of the live load. And then to see the actual stress, you have to use this ratio also. That is the air's requirement and the area of steel provided. So once you use this equation, 2243 divided by 2412, that is the area provided, this is the requirement, and the vertically downward load is 1000 kilonewtons, and the live load is, or the variable load is 350. So 350 multiplied by 0.3 divided by the full load, and that is 1875, and that will give a value of 238. And when you have this value of 238, this table is exactly the same as that is given in EC2 as table 7.2. And you can see if the stress is 238, the maximum bar diameter is 16 millimeters. Maximum bar diameter that you can use to ensure that the crack width remains at 0.3 millimeters or less is 16 millimeters. So actually in this problem, what is used is 16 millimeter, and that means it's adequate. And on the other hand, if you like to use a greater diameter, then you have to reduce the steel stress to this value by providing either additional reinforcement or by changing the depth of the section or doing something. You have to actually reduce the stress. On the other hand, you can actually go with a smaller diameter. So the general rule is It's always preferred to have larger number of small diameter bars than fewer number of large diameter bars, unless the large diameter bars also will result in closer space. So once you have the reinforcement and check for crack controlling, then you can check it for punching shear. And for punching shear, we have to check the steel ratio in both directions. And the steel ratio is about 0.165 or 0.17, 0.0017. And so basically, for this ratio, if you look at the shear carrying capacity, you can look at the shear carrying capacity. The steel ratio is less than 0.25, and the thickness of the section is 520. So a value slightly less than 0.4 is there. So what is used is 0.4, and so the shear resistance will be 0.4 newtons per meter squared. So the punchy shear resistance will be 0.4 multiplied by UD, and that will give a value of 1691 kilonewtons, whereas the punchy shear force we have calculated earlier as 626 kilonewtons. The punchy shear force has been calculated as 626 kilonewtons, whereas the punching at that particular perimeter, the punchy shear resistance is 1691 kilonewtons. So what this shows is there's no chance for punching shear failure, and because there's no chance for punching shear failure, this is okay. Then we have to check for direct shear, and the direct shear is checked an effective depth away from the face of the column, and an effective depth away from the face of the column is at 0.52 meters away, and this is 1.2 meters. 1.2 minus 0.52 is 6.68 meters. So the the direct shear force will be 239 multiplied by the width of the base, 2.8 meters, and this length 0.68. So that is the direct shear force, and the direct shear force will be 239 multiplied by 2.8 into 0.68, 455 kilonewtons, and we know the strength of concrete is 0.4, and so if the strength is 0.4, what is the direct shear force carrying capacity is 0.4 into 2800 into 500 into 10 to the power minus 3, 582 kilonewtons, whereas the direct shear force is only 455 kilonewtons, which means we do not have to provide any shear reinforcement. The thickness selected is adequate to resist shear. Resist direct shear and punchy shear both, and also we have to provide bottom bars of 16 millimeter at 225 centers in both directions. So when you are doing these calculations, earlier when you're looking at the size of the base, we actually made an allowance for the size of the base. So when we looked at the size of the base, we said, okay, we are going to allocate 150 kilonewtons for the weight of the base, So on the other hand, rather than using the weight of the base, you can say the effective bearing capacity is 150 minus the pressure due to weight of the base. 150 minus the pressure due to weight of the base. So instead of assuming a footing weight of 150 kilonewtons at the start of the example, it's possible to allow for the weight of the footing by having a net safe bearing pressure. Net safe bearing pressure or net bearing pressure. And for that, what we can do is we can reduce the bearing capacity 200 minus height of the base multiplied by the unit weight of the base. And so you can see 200 minus 0.6 times 25 gives a value of 185 kilonewtons per meter squared. So we could have used the actual loads and divided by the net safe bearing pressure of 185. Then again you will end up with a similar answer. So either you allow for the weight of the base or you adjust the bearing capacity to cater for the weight of the base. So that way you can actually design a base easily. And in a base, there's no need to provide top reinforcement. There is no need to provide this type of top reinforcement. And unless you suspect that the amount of concrete involved is too much, that there can be some kind of thermal cracking. There's a possibility for thermal cracking that occurs only in a very heavily loaded large column bases having a greater thickness. Then you can provide some nominal reinforcement here. Otherwise, no need to provide any top reinforcement. But the important thing is beyond this phase, this reinforcement should be properly anchored. And in addition to that, when you are getting these vertical bars, you have to bend them and place the vertical bars in such a way that it rests on the bottom mat. So those are the important things about pad footing. And but this particular pad footing is subjected to a vertical load only, and there's no bending moment acting on the section. So we'll take a break now, and after the break we'll discuss how to deal with a pad footing subjected to axial load and a bending moment. And we will also look at how we deal with the punchy shear resistance, because when you have a axial load and a bending moment, what happens is the stresses are varying everywhere. Stresses are varying everywhere. So on one side you get higher soil pressure, on the other side you get lower soil pressure, but we have a punchy shear perimeter which goes right round. And so how do we deal with this variable pressure under the base in case that the footing is subjected to a vertical load and a bending moment so that it will cause non-uniform stress distribution below the base. So we'll have a look at this in a moment, but shall we start around 10 past 3, and then we'll discuss this particular topic. So Indranil, any questions? Anybody wanting to ask any question? I discuss it in little detail because we'll be making use of the same method in other ones as well. So I will stop here, and then we'll meet at 3:10.